So today we discuss determinants of the matrices. So a general M cross N matrix can be represented by with M rows and N columns. First row, second row, so on. So mth rows. So it means in this matrix there are M rows and N columns. So that is why the order of this matrix A is Mn or M cross N. Double subscripts are used to identify the number of the rows and the number of the columns. For example, if we have A11, so it means this is the entry of first column and first row. And similarly, if we have the entry A23, so it means second row and third column. For example, A23 is the entry at the intersection of the second row and the third column. So in general, the entry at the intersection of row I and column J is denoted by Aij. So Aij means the entry of the matrix at ith row and jth column. So this is easy to remember. Entry of the intersection of row I and column J is denoted by Aij. Okay, so next is a square matrix is one that has the same number of rows as column. So if we ask someone that what is the square matrix, we can say a square matrix is the matrix whose number of column is equal to number of rows. Or we can say a square matrix is one that has the same number of rows as columns. Each square matrix A with real number entries can be associated with a real number called the determinant of the matrix. So it means every square matrix can have determinant, and determinant is a real number. So a square matrix is one that has the same number of rows as columns. Each square matrix A with real number entries can be associated with a real number called the determinant of the matrix. So determinant can be denoted with absolute value of A. You see, absolute value of A. So it means if we have a square matrix whose entries are real numbers, so then determinant of this matrix is also a real number. We will first define determinant of 2 by 2 matrix. So it means the 2 by 2 matrix has 2 rows and 2 columns. Okay. So what is the definition? So if A is equal to A11, A12, A21, A22, so this is a matrix of order 2 because it has 2 rows and 2 columns. Okay, so now how we can find the determinant? We need to multiply first diagonal. So we will multiply A11 with A22. Okay. We multiply A11 with A22 and then we will subtract the entries of the other diagonal. Okay. So then subtract A12, A21. So multiply A11 with A22, then minus sign and then A12 and A22. Okay. Here is an example. So if A is equal to 3 minus 2, 5, 8, how we can find the determinant of this matrix? We will multiply the first diagonal. We will multiply 3 into 8. And what we will get? 24. So then we will put minus sign, this minus sign, and we will make use of the braces. to avoid from the mistakes. So if we don't use brackets, we can do mistake. And then, so we will multiply 5 with 2. 5 into 2, 10 with minus sign. So this minus and minus will be plus. So it will be plus 10. So 24 plus 10 is equal to 34. So it means determinant of this matrix is 34. So just if you observe, the entries of this matrix are real numbers. 3 is a real number, minus 2 is a real number, 5 is a real number, 8 is a real number. Then multiply 8 with 3, we will have 24 is again a real number. Minus into minus plus 5 into 2, 10. So 24 plus 10 equal 34. So it is a real number. Okay, so it's mean if a matrix have entries as a real number, so then its determinant is also real number. So next is another example. So just it is also the matrix of order 2 by 2. So we will do the same procedures. We will multiply minus 3 with 8 and we will have this minus 24. Then minus is the convention. Convention mean it's a rule to put minus here. Okay, so then we will multiply 2 into 6. So we have a 12. Okay, and minus 24 minus 12, we will have minus 36. To find the determinant of 3 by 3 matrix or larger square matrices, it is convenient to introduce some additional terminology. Okay, what are these additional terminology? So if A is a 3 by 3 matrix, then the minor denoted by Mij of the entry Aij element is the determinant of the 2 by 2 matrix obtained by deleting row I and column J of A. Okay. So we can revise it. What is the minor of matrix? So minor is denoted by Mij for the entry Aij. It means each entry of the matrix has a minor. So if entry is Aij, the minor will be denoted with Mij. And how we can calculate this minor? We will delete ith row and jth row. So if a matrix is of order 3 by 3, the minor order will be 2 by 2. And if a matrix will be of order 4 by 4, minor could be of order 3 by 3. Okay, let's consider what is the minor. So just see here, the matrix is of order 3 by 3. So first row, second row, third row. First column, second column, third column. So 3 by 3. Find number 1, M11. So minor of the entry 1 1. And B minor of the entry 2 3. So what is the entry 1 1 is 2. And what is the entry 2 3 is second row and third column is minus 2. So we will have to find two minors for two different entries. First entry is 2 and the second entry is minus 2. To find M11, we first delete row 1 and column 1 of matrix A. Okay, so delete this because we are calculating the minor of entry 2, 1, 1. So delete first column and first row. We will have a minor 3 minus 2, 2 and 5. So this is actually a matrix with reduced order. Original matrix is of order 3 by 3 and the order of the minor is 2 by 2. So then we will calculate determinant of this matrix. So what is the determinant of this matrix? 3 into 5, 15, minus, then minus 2 into 2, 4. So 15 plus 4, 19. So 19 is the minor of the entry 2. So this entry 2 and is denoted with M11. Okay, so next is to find M23. So minor of the matrix, minor of the entry at position second row and third column. So what is this entry? Minus 2. So we will delete row, second row and third column. So what will have the matrix? 2, 1, 4, 2. And then if we calculate determinant of this matrix, we will have 2 into 2, 4, minus 1 into 4. Okay, so 4 minus 4, 0. So it means minor of this entry minus 2 is 0 and minor of the entry 2 is 19. Okay, so then we will move next. Following definition will also be used. If A is a 3 by 3 matrix, then the cofactor denoted by Cij of the element Aij is defined by minus 1 I plus 1 Mij. Okay, so what is the difference between minor and cofactor? So if we multiply minor with minus 1 power I plus j, we will get cofactor. So if we have a matrix A is equal to 3, 2, minus 4, 1, 5, 4, 2, minus 3, 1. So order of this matrix is 3 by 3. So find C32, it means we have to find the cofactor of the entry at third row and second column. So what is the entry? Minus 3. Third row, second column. So this entry is minus 3. So first we will calculate minor of this matrix. And to calculate minor of this entry minus 3, we have to delete second column, third row. And then we will have minor 3, 4, minus 4, 1. Okay, 3, 4, minus 4, 1. And we will calculate determinant. So it's calculating the determinant as 4 into 3, 12. Okay. And this minus sign, minus 4 into 1, minus 4. So 4, 12 plus 4, 16. Therefore, C32 is equal to minus 1. So what is the minor of this? So calculating the cofactor, we just has to multiply with minus 1 and power of this indices. So what is the indexes? Our indices is 3, 2. So we can just add 3 plus 2. We will have this minus 1 power 3 plus 2 is 5. So because the power is odd number, so we will have minus sign. If the power is even number, so then this minus 1 will be positive. Okay, so now the power is odd number. We have this minus 1. So minus 16 is the cofactor of the entry minus 3. So similarly, we can find cofactors of all the entries of this matrix. The concept of a cofactor can be used to define the determinant of a 3 by 3 matrix as follows. So if we want to calculate the determinant of the matrix, so we can actually find a cofactor and it will be easy to find the determinant. Okay, so how we can find the determinant of matrix of order 3 by 3? So A11 and then what is the cofactor? So cofactor is This minor is A22 A3 minus A23 into A32, and then we can add minus 1 power this A1 plus 1. So if we multiply this, so just remember A11 is the entry at the first row and first column. A21 is the entry in the first column and second row. A31 is the entry in the first column and third row. So we can make expansion of by first column or by first row. So it depends on the student or the user, so on his preferences. Okay. So now we can compute the determinant of this 3 by 3 matrix. Okay. 3 rows and 3 columns. So we want to verify whether this statement is true or not. Okay, we can write this statement as it is. So then A11 is minus 2, and then cofactors minus 1 power 1 plus 1, and then this minor 0, 5 minus 4 minus 6, then plus 3 into minus 1, 2 plus 1, 1, 4 minus 1 minus 6, then plus 1 because we are expanding with the first column. So minus 1, 3 plus 1, 1, 4, 0, 5. Okay, so determinant of this one is a 0 plus 20. So 0 plus 20 is 20. So minus 2, then minus 1 power 2 is 1. So minus 2 into 1 into 20 plus 3, and then minus 1 power 3 is minus 1, then 6 minus 6 and plus 4 minus 6 uh, plus 16. Okay, then we will have 10. Similarly, this plus 1 and minus 1 power 4 is also 1. 5 into 1, 5. So this is plus 5 minus 30 minus 40, and we have the determinant of this 3 by 3 matrix is minus 65. Okay, so that is the way to find the determinant of 3 by 3. So what is the way? So just we can expand by first column or by first row. So by first column, so A11, A21, A31. And then we will find cofactors of these entries. A11, A21, A31. Okay, so A11 is minus 2, A21 is 3, A31 is 1. Then minus 1 power, okay, 1 plus 1, so 1 plus 2, 1 plus 3. 1 plus 3 is even, and 1 plus 1 is even. So here minus 1 will be changed into positive. Okay, so here will be positive and here will be positive. But here 2 plus 1 is 3 odd, so this will remain as negative. Okay, so this is negative, this is positive, and here minus 1 become positive, but due to minus 2, it will remain as negative. So that is a simple way. So when we use definition, we often say that the determinant is being expanded about the first column. It can also be shown that any row or column can be used to expand a determinant. For example, for matrix A in example 5, the expansion of the determinant about the second row is as follows. So it means we can expand about any row or any column. So it's not a problem. So here the expansion is being done with respect to second row. So second row is 3, 0, 5. Okay. So now we can expand by second row. So 3 Okay, then minus 1, what will be the power? Second row and first column. Power will be 3. Then 0 and minus 1. This entry is at the position second row and second column, so that's why 2 plus 2. Then 5, so this entry at the position second row and third column, 2 plus 3. Okay, so 3 into this will be negative minus 1, this will be positive 0, 1, and then this will be negative 5 into minus 1. And okay, so to compute the minor of this 3, we will delete this second row and first column. The matrix will be 1, 4, minus 6, minus 4. And the determinant will be minus 6 into plus 16, 10. So then for this entry 0, we will delete second column and second row. And the determinant will be minus 2, 4, 1, minus 6. Minus 2 into minus 6 will be 12. Okay. And then minus 4, 12 minus 4, 8. So then for the entry 5, we will delete third column and second row. The matrix will be minus 2, 1, 1 minus 4. And then we will calculate the determinant. 4 into 2, 8, minus 1, 7. So then 7 into 5 minus 35, 0 into something 0, and 3 into 10, 30 minus 30. So minus 30 minus 35 minus 65. So if you observe, answer is the same. It means we can expand with respect to any column or any row. Okay. So then note that when we expanded about the second row, the computation was simplified by the presence of a zero. In general, it is helpful to expand about the row or column that contain the most zeros. The concepts of minor and cofactor have been defined in terms of 3 by 3 matrices. Analogous definition can be given for any square matrix, that is, any n cross n matrix with n greater than or equal to 2, and the determinant can then be expanded about the row or column. Certainly, as the matrices become larger than 3 by 3, the computations get more tedious. We will Okay, so next is the properties of the determinant. So these properties are very useful to evaluate the determinant directly without using expansion. And what is the first property is that if any row or column of a square matrix A contains only zeros, then determinant of this matrix is equal to 0. So this is the point to be remembered. So if all entries of any row or any column is 0, so then determinant is 0. Okay, so the second property is if square matrix is obtained from square matrix A by interchanging two rows or two columns, so then determinant will be multiplied by minus 1. Or we can say that if a square matrix B is obtained from square matrix A by interchanging two rows or two columns, then determinant will be multiplied by minus 1. So, or we can simply remember that interchanging of two rows will multiply the determinant by minus 1. So it's simple. So first we can have a look of these properties and then we will discuss. Property third is if square matrix is obtained from square matrix A by multiplying each element of any row or column of A by some real number k, then determinant of this B is actually the determinant of A multiplied by k. Here we can say that if any row or any column will be multiplied by k, then the determinant will be multiplied by k. So simply we can remember that if any row or any column of a matrix will be multiplied by k, then its determinant will be multiplied by k. Then for the fourth one, so fourth property is if square matrix B is obtained from square matrix A by adding k times a row or column of A to another row or column of A, then determinant of A is the same as determinant of B. So it means if we add k times a row or column to another row, so there will be no change over the determinant. So adding k times a row to another row will not affect the determinant of a matrix, we can say like this. And the fifth property is if two rows or columns of a square matrix A are identical, then determinant is 0. So it means if two rows or two columns are same or equal, or every entry of the one column is equal to the second column or first row equal to the second row, then its determinant will be 0. Okay, so these are the 5 properties. So I think it should be the 7th, but okay, 5s are enough. Now we can discuss these properties one by one. Okay, the first property is simple. So what is the first property? If any row or any column of a square matrix have zeros, so then the determinant is 0. And the second property is if square matrix B is obtained from square matrix A by interchanging two rows or two columns, so then determinant of B equal to minus determinant of A. Okay, so this we can verify that this is here is a matrix. So 2 5 minus 1 6. So just interchange these two rows. So we will have minus 1 6 2 5. So now what is the determinant of this matrix? A is 17 and determinant of this matrix B is minus 17. So it means interchanging of two rows or two columns will multiply the determinant by minus 1. And this third property is square matrix B. If we obtain from a square matrix A by multiplying each element of any row or column of A by some real number k, then determinant of B is equal to kth time determinant of A. So this property can be verified. So suppose we have a matrix of order 3 by 3. So what is the determinant of matrix A? Determinant of matrix A is minus 168. Okay. So now if we multiply this matrix B is for multiplying each element of a third column by 1 by 4. So what is the third column? Third column is 8, 12 minus 16. So multiply third column with 1 by 4. So we will have this 2, 3 minus 4. So 8 divided by 4, 2, 12 divided by 4, 3, minus 16 divided by 4, minus 4. Okay, so then what is the determinant? Determinant is minus 42. So it means this 168 is divided by 4. So divide by 4. 4 4s are 16, then 4 2s are 8. So minus 42. We see that so this determinant of B is actually equal to determinant of A divided by 4. This example also illustrates The usual computational use of property 11.3. We can factor out a common factor from a row or column and then adjust the value of the determinant by the factor. For example, so from the first row, you can say that you can take 2 as a common from the first row. So 2 multiplied by 2, 1, 6 multiplied, 6 divided by 2, 3, 8 divided by 2, 4, okay, and 2 divided by 2, 1. So in this way, we can have this. So factor a 2 from the top row, okay. So this top row is 2, 6, 8, and if we divide this top row with 2, we have this 1, 3, 4. Okay. So then this next property is if square